Hi everyone, today I'm going to talk about differential geometry in backpropagation. The reason for this topic is that when I was learning backpropagation as an undergrad, there were always a few things about backpropagation that seemed strange to me, and I will verbalize what are the strange things and how I went about resolving them, having learned some tools from differential geometry. The setup for backpropagation is that it is used in machine learning so that we can train better models. Usually in machine learning, we have a model that is parameterized by a set of weights, theta. This theta belongs in the space of weights, which I usually denote by capital theta. And for our purposes, usually this capital theta is always Rn, where n is a very large number. Let's just suppose we are in the supervised learning context where we feed in data. We have data xi and yi. We have paired data where we know the true label. So this yi is the true label for xi. We passing xi to the model. We want the model to predict the value of y. The model will spit out a prediction value, which is yi hat. And then because we know the true value of yi, we can have a loss function that takes in the prediction and the true value and spits out a real number, a scalar loss for us to compute. So this loss will map yi hat yi to some number, let's say 0.739. You can think of this loss function as, for example, MSE loss. But what is important is that it produces a scalar value over here. This scalar value is a measure of how well the prediction is. If our prediction is very close to the true value, so if yi hat is very close to yi, then this loss should be as close to zero as possible, or maybe as negative as possible. This loss function, because it is a scoring mechanism, the model should learn to minimize this loss, because minimizing the loss means that the model is better at predicting, which is what we want. So this process of backpropagation allows the model m theta to update its weight to predict better. So you can think about it as at time step t, the model has weights, let's say theta t. At time step t plus 1, after we fed in batches of data, we expect the model to be better at predicting. We expect the model to have theta t plus 1, which is theta t plus some update, right? This is the update from backpropagation. This may seem slightly abstract, so let us ground the discussion in PyTorch. Let us consider this set of equations, z equal to x times y, and then let's say the loss is just z plus x, right? We purposely used x 2 times here to illustrate what will happen. In PyTorch, all these x, y, z, l are all tensors, and they have type torch.tensor. In the forward pass, PyTorch will build up a computation graph. What is a computation graph? A graph usually have nodes and edges. In a computation graph, the nodes are actually the operators. So the multiply, the plus, the edges are actually the input and output to the operators. So given our simple setup, we can draw the computation graph that is built up in the forward pass as such. We start off with a multiplication node. X is fed in as an input here, right? Y is also fed in as an input, and the output is Z. Next, we have a plus operator. It takes Z as the input, it takes X again as the input, and it spits out L, which is the loss. So this is the computation graph that is built in the forward pass. So we have to talk a bit more about PyTorch internals to understand what else happens in this forward pass. Recall that I've mentioned that x, y, z, l, they are all torch tensors. As torch tensors, they have a few attributes. There are two important attributes that are particularly useful in the discussion of backpropagation. One is the dot grad attribute. The name is called dot grad, so one can expect it to be some sort of gradient. We can interpret this dot grad as a gradient. It is also a torch dot tensor, meaning it is also a tensor, and we expect it to have the same shape as the tensor that we are taking the attribute of. One thing that I want to clarify here is that this dot grad is actually either a tensor or a none. We only care about its gradient if it is actually registered in the computation graph, right? So for our purposes, we assume that all the tensors are registered in the computation graph. There are some tensors that we don't really want to register in the computation graph. For example, the data would not be registered in the computation graph because we would never want to update our data. It is not useful. We only want to update the weights in our model. So this dot grad is either a tensor or a non-variable. And when it is a tensor, we expect it to have the same shape as the tensor itself. In other words, if I call x dot grad, I would expect x dot grad dot shape to be equal to x dot shape, provided that x dot grad is not a none. This allows us to update x. You can imagine x here as a weight in the neural network. And to update the weight, we expect the update to have the same shape as the weight. So the second property that I want to mention is this dot grad func property. This is the reason why backpropagation work. Let us just take this subgraph as an example. So in this multiplication node, we have x as an input, y as an input, z as an output. In the forward pass, when z is computed, z.gradfunc will be populated with a function that is something like a mul backward. What is this mul backward function? Well, it is actually a pointer to a C++ function. This function takes in the gradient of the output and transforms it into the gradient of the inputs. In particular, in our case, in the backward pass, you can imagine that the gradient of the loss with respect to z is coming into this multiplication node. And what we want to happen is that the gradient should propagate into the inputs. So we want partial L over partial X to be propagated to the X edge, and we want partial L partial Y to be propagated to the Y edge. This allows X and Y to both be updated. Z over here is an intermediate variable. We don't really care whether we update it or not. What we want to update is the model parameters. I guess I should clarify over here that X and Y are the trainable parameters. Z is just some intermediate variable. Similarly, L over here is actually the loss, which is also kind of an intermediate variable. We don't want to update the loss. We only care about updating the trainable parameters. I hope this makes sense. Yeah, so let's just ground our discussion in the PyTorch framework, right? We can actually look at how PyTorch do things. Let's just first import torch. Let's suppose X is some. Let's just stick to our example, right? It is a tensor of size 2, 3. We have to pass in this argument requires grad so as to register it in the computation graph. Similarly, we define y to be a compatible tensor. So same shape because we are going to multiply it with x. And we can compute z is x times y. This times here will be element-wise multiplication. So we should expect z.gradfunc to hold a function that is multiply backward, right? You can imagine all these grad function as remembering the function that produced the tensor. So in this case, z.gradfunc is the backward function corresponding to the function that produced z. So z.gradfunc is going to be a mul backward as expected. Following our example, we can call loss as the sum of the elements in z. When we call loss.gradfunc, loss is also a tensor. So loss.gradfunc will be the backward function corresponding to the operation that produced this loss tensor, which is sum. So it will be sum backward. And we can look at, for example, x.grad. It will be none because we haven't initialized the backward process yet. We can call y.grad. Similarly, it will be none. If we look at loss, because we summed over the elements in Z, it should be a scalar, which is precisely what we want in the machine learning context. So this loss is going to be a scalar tensor. You see that it even prints out the grad func in the representation. And when we call loss.backward, it will initiate the backpropagation process. Now we can look at x.grad, and you can see that x.grad's shape is precisely 2, 3, right? It has the same shape as x. X.shape is also 2, 3, and y.grad would also have a shape of 2, 3. If you look at x.grad func, it should be a non-variable. Y.grad func is also a non-variable because x and y, there's nothing producing them, so they don't actually hold a grad func. So there's a cool exploration. Let me just draw the computation graph again here because I want to talk about more things. We have seen just now that x.grad func is none. And this is because x, y are input to the computation graph. So a bit of PyTorch terminology here. We usually refer to the output variable as the root of the backward graph. And we refer to the inputs, so in this case, x and y, as the leaves of the backward graph. I sometimes also call them leaf tensors. You can see why this is the case because from the view of the backpropagation algorithm, we start off at the back, right? We are passing in partial L over partial L equal to 1, and we are expecting this derivative to backpropagate through the computation graph. So in this case, it will backpropagate through this plus operator into this arrow and this arrow. It will have partial L, partial X, and partial L over partial Z. When it is feeding into this multiplication operator, it will backpropagate again from partial L, partial X, and partial L over partial Y. From this view, it is really starting at the root, which is the loss tensor, and backpropagating it to the leaf tensors, which are the inputs. And the leaf tensors are usually the trainable parameter of the neural network. And notice there's an interesting bit, which is there are two edges feeding into X. From our courses in calculus, we know that these two should be summed together. The reason is because we want to update X. We care about the total derivative of the loss with respect to X. To get the total derivative, we are summing up the components of contributions of X to the losses. X contribute as an input to this multiplication node. It also contribute as an input to this addition node. What PyTorch does is that for a leaf tensor, actually over here, I want to say some more things. So a leaf tensor in PyTorch, the definition is X, which is a torch tensor, is a leaf tensor if x.grad func is none. X.grad func is none just means there's no operation that produces that tensor, which is why it is none, right? There's no backward operation to take of a non-existent operation. So x and y here are leaf tensors. So back to the sentence that I was saying, for a leaf tensor, PyTorch implicitly adds an accumulate grad node. So this is added in C++, I believe. Yeah, I think this is added in C++. So there's actually a phantom node here whose job is just to, as the name suggests, accumulate the partial derivatives that is passed into it, right? Because all the partial derivatives have the same shape, they can be just added together. And at the end, to complete the training loop, usually we have an optimizer. We register the trainable parameters in this optimizer, and we call optimizer.step. What this .step does, you can just think of it as x is equal to x minus a learning rate. So this is a learning rate, e.g. like 1e minus 3 times x.grad. Why is it minus? Because x.grad points in the direction of steepest ascent. X.grad has the same shape as x, which is why they can be just subtracted. I hope this gives a good overview of backpropagation. Now to the actual thing that I want to talk about, which is there are actually two sources of strangeness over here. Or back when I was an undergrad, I always felt that there are two things that are very strange, and I want to illustrate what is strange about it. So firstly, we are using the words derivatives and gradients too interchangeably. You might think like, why do I even care about this? The reason is because if we mix up these two definitions, there is bound to be confusion, right? So if I were to draw the computation graph again, when we are doing our back propagation, partial L over partial L is equal to 1. What precisely is this thing that we are passing back? From the perspective of derivatives, we understand derivatives as sensitivity. So this 1 represents that at this moment, if I were to increase my loss by delta L, I would expect my loss to be increased by delta L. Right? You heard that right. I said the same sentence twice because that is precisely what is happening here. The dl that is appended to the loss is partial L dl, which is 1 times dl. This is exactly right. From the perspective of gradient, if, let's say, the computation graph just ends here, then what does this really mean? It just means that we should update our loss by 1, right? Isn't optimizer.step just appending the gradient to the tensor itself? Suppose we impute the computation graph at the loss. Loss.backward followed by optimizer.step, it will decrease the loss by learning rate times 1, which is the learning rate. Is that what we want? We are interpreting this sensitivity as the gradient. And I hope you can see why that is going to be kind of a problem, right? If we are taking a step of size 1, sure, like we are scaling it with respect to some learning rate parameter. But this 1 is not exactly negligible, right? It is saying we want to go in the direction where we want to change the loss by 1. That is going to correspond to a lot of different updates of weight, right? A lot of updates of weight when passed through the network can give a loss update of 1 or minus 1 because it is not exactly an infinitesimal quantity. The backpropagation of these sensitivities only work, or the theory only work precisely because all of these functions locally, they are linear transformations, which is why we are passing back this sensitivity and we can propagate it through. Yeah, so my point is that because we use derivatives and gradients too interchangeably, it results in quite a lot of confusion. The right way to think about it is actually to think about it in derivatives. But because PyTorch uses .grad, many people, including me, thought that this should be thought of as gradients. And that is a pretty big hole to fall into. So the second point of confusion is that how do we construct the backward function of an arbitrary function f? Meaning, if z is equal to f of x, y, given partial loss partial z, how do we get partial L partial x and partial L over partial y? For those of you who are familiar with Jacobian, you'll probably see this formula, which is to backpropagate, we just need to take the transpose of the Jacobian of f at the particular inputs x and y, apply the transpose of the Jacobian to the sensitivity. This will give us partial L partial x and partial L partial y, depending on how you bundle your tensors together. We are pretty familiar with this Jacobian being a matrix, but often case in machine learning context, our functions are multi-dimensional tensors, right? So let's just give a simple example. Let's say A is equal to A W B, where W is our trainable parameter. Trainable parameter. Let's say W has shape R m by n, right? And A has shape R, let's say P by m, B has shape R m by q. So AWB will have shape P by q, which is precisely the shape of Z. The question is, given partial L partial Z, how do we get partial L partial W? So for those of you who are familiar with this Jacobian transposed, you will think that all this involves is just multiplying this by a matrix. But partial L partial Z, if we look at it from the shape of a gradient, right, this should have exactly the same shape as Z. So this should have shape RP by Q. We should expect it to have the same shape as W, which is R m by n, right? So you can't really have a matrix that converts between these two, right? Your Jacobian somehow becomes a map from a multidimensional tensor to a multidimensional tensor. I think this confused me a lot back when I was learning machine learning. Before I learned all the differential geometry tools, the way I used to do it is this. We use the heuristic of shape matching. We are given partial L partial Z, and we want to get a shape of R m by n, right? If you look at the shape, the only way this is possible is to do the following construction, which is you take the gradient of the output Z, partial L partial Z, you left multiply it with A transpose, you right multiply it with B transpose, and you would just call this as partial L partial W. And this is correct. Why does this heuristic work? Firstly, it measures the shape. Secondly, you expect this mapping to be a linear mapping. And left multiplication by A transpose and right multiplication by B transpose is precisely a linear transformation. But this is very unsatisfying. You can also get by this with infinitesimal analysis. You have Z is AWB, you have Z plus DZ is equal to AW plus DWB. So I hope this makes sense. Given a change in W, let's say delta W, how does your output change? It changes by delta Z. Let's suppose now we consider the loss, right? The loss is some function of Z. So a change in the loss, by Taylor's theorem, it will be equal to the inner product of the Jacobian partial L partial Z and the change in Z. Note that I use inner product here. The reason is because delta Z, right, it has the same shape as Z, so RP by Q. The Jacobian, no matter what it is, it needs to output a scalar at the end, right? Loss is a scalar. So there is going to be some inner product going on. And in this case, it is just the element-wise product. So we can write this as the trace of partial L partial Z transpose delta Z. In Euclidean space, this is the Frobenius inner product, which is just the multiplication of the element, then you sum them together. What we can do here is we can substitute this delta Z with A delta WB. So this will give us the trace of partial L partial Z transpose A DWB. Then, we can apply some trace properties. The trace is cyclic with respect to the order of operands inside. So we can bring this B over and we can write this as the trace of A transpose partial L partial Z, B transpose, the whole thing transpose delta W. And this is equal to the inner product of A transpose partial L partial Z, B transpose delta W. You note that we had this definition, right? The change in loss is the inner product of the Jacobian of the loss with respect to the intermediate Z and a change in Z. And we express it in terms of the inner product of something with respect to a change in W. So by definition, this is precisely the partial L partial W that we are looking for. So we've actually have a proof that partial L partial W is A transpose partial L partial Z B transpose. So if we're coding up the backward function in the PyTorch kernel, we'll precisely be coding up this equation, right? How it transforms the gradient with respect to the output to the gradient with respect to the input. But the question that I always had is, why are we doing this? Both ways feel kind of unnatural. right? If we were to do it by the heuristic of shape matching, it is not rigorous. Surely you can't get away with everything by shape matching. What if some dimensions are the same? You're going to get very confused. And the second way, it seems like we are doing a lot of mathematical somersaults just to get this final term. And we even went back to the basics, which is we tried to do infinitesimal analysis. And that is really something that is done in the forward propagation, right? Infinitesimal analysis resembles forward propagation, where we need to trace out the whole computation graph. Why do we need to be aware of this function f to do our work that should only concern the kernel itself? I hope all this talk has at least alerted some people that there are some strangeness in the understanding of autograd if we are not careful with some terminologies. And so recently, I have been just thinking about this, and I was also reading up some materials in differential geometry, which is how I come up to a resolution for the two confusions above. I just want to introduce some differential geometry tools, and I will introduce it from the perspective of an applied mathematician. We only need the things sufficient for understanding this, for resolving these two confusions. Firstly, I want to talk a bit about Taylor's theorem. Right, we are very familiar with the one-dimensional case, which is saying, well, given a function f, let's suppose we perturb the input by a bit, let's say delta x. This will give us to the first order fx0 plus f prime x0 times delta x, right? So this is a times. We assume f is just a simple function, univariate, r to r. This is just a times. And this makes sense. Now let's upgrade the difficulty. Let's say our f is a function from Rm to Rn. You'll say something like, sure, we learned that in multivariable calculus, right? So fx naught plus delta x is just fx naught plus the Jacobian of the function at x naught, right? jfx naught times delta x. So we are really relying on this Jacobian being a function that transforms delta x is in Rm, right? It lies in the input space. We are relying on this Jacobian being a function that transforms our Rm vector into our Rm vector. So usually you see as a matrix that is m by m. Now let's upgrade the difficulty again, right? What if f is r, let's say m by n, and it goes to r m by q? You'll say something like, sure, we can just flatten the coordinates, but that is a very messy way to think about it. The thing I want to mention here is that this Jacobian term is really interesting, or this derivative term, right? So what is the Jacobian of f? So we understand it as some sort of gradient, right, of the function at that point. But firstly, we have to evaluate it at a point. This is the reason why we call it f prime x naught, because we need to evaluate the gradient at a point in our input space. So if f is a function from the input space to output space, let's say the input space is denoted as calligraphic x and the output space is denoted calligraphic y, then the Jacobian of f is a function that takes in an input from x because we need to evaluate the derivative at some point. And then in the one-dimensional case, it is multiplied with a delta x. In the two-dimensional case, it is multiplied with also a delta x, but it is something in Rm, right? So it might be tempting to say that the Jacobian, it takes in the point to be evaluated at, and it returns a function that takes in something in the input space and gives out something in the output space, right? So this is our x naught, this is our delta x, and this is our delta y. So in our end, this observation works. But in differential geometry, we have to be more precise. The thing to note here is that this x naught and this delta x are not really the same object. Delta x, we regard it as a change between 2 points in x, whereas x is just an object in space x. Similarly, this y over here, delta y is an infinitesimal change in y. in differential geometry, we have to be precise about this. And I think it is right to be precise. We usually label it with a T in front. I will explain more about this later on, but for now, I just want to impress the fact that x naught and delta x, we should by right think of them as living in two different spaces. Because one is actually living in the input space, the other is an object that denotes an infinitesimal change in the input space. Actually, that is a pretty good point. So as the second part, I will introduce what we call the tangent space. So in differential geometry, we have this object called the manifold, and we usually denote it as M or N. I will not define manifold because it takes a lot of groundwork just to define it precisely. And remember, we are applied mathematicians, so we just care about the things that resolve our confusion. But the physical picture is important, right? What is a manifold? I always think about it as a curved surface in space. Usually, this is enough for me to understand what a manifold is, right? It is just some curved surface. Let's say we are at this point X. Let this manifold be M, right? So you can think of this M just being our input space. And a point X lies on this manifold. What is delta X over here? Remember what I said about X and delta X being possibly living in different spaces? This is exactly where you'll see it. What are the possible delta X? Well, you can go infinitesimally here along the manifold, infinitesimally here, infinitesimally here, infinitesimally here. But if you actually take that infinitesimal step, you might not actually end up on the manifold, right? The manifold is curved. So for example, just for us to see it clearer, if this is a cross-section of our manifold and our point X is here, then our infinitesimal movements would be something like this, right? It will be something like this. But if we actually take that infinitesimal movement, we will just be off the manifold. Which is why just now I said that x naught lives in M, but your delta x actually lives in what we call the tangent space, right? The tangent space is a different space than the manifold. I should be more precise. So this delta x needs to be defined with respect to a point, right? And this tangent space, for now, I will define it as with respect to a point. So the tangent space to the manifold M at x naught, right? So let me just write here, Tx naught M, we call it as the tangent space to manifold M at point x naught that belongs to M. So in this case, the tangent space will be this plane or some whatever you visualize geometrically as the tangent. So this is the tangent space at x naught. So I hope this clarifies that delta x and x really live in different spaces. One thing I want to note here is that tangent spaces are vector spaces. I hope that this is obvious and don't need me to prove it concretely. This is because if, let's say you have x as a tangent vector, c times x is also kind of like a tangent vector, right? Tangent to the manifold at that point. If you have two tangent vectors, the sum of them should also be a tangent. Two, Jacobian now becomes linear transformations between tangent spaces. So I should be precise. So what I mean is Jacobians evaluated at a point is a linear transformation between two tangent spaces. What does this mean? So let's say we have two functions, m that goes from manifold m to n, and g that goes from manifold n to, let's say, p. We can obviously compose them, right? G composed with f will be a function that goes from m to p. The Jacobian of f, so remember when we do the Jacobian, we have to evaluate it at some point, right? So let's say we have x naught that is in m. The Jacobian of f at x naught is a function that maps from the tangent space to m at x naught to the tangent space to n at f of x naught. Let's suppose our input manifold is this curved surface and our output manifold is, let's say, this curved surface. X naught is here, it gets mapped to a point, let's say f x naught here. A tangent vector here would you would imagine if things go right. Actually, you don't have to imagine it is right. Mapped to a tangent vector in the output space. For all our machine learning discussions earlier, this is really saying infinitesimal change in the input will lead to an infinitesimal change in the output. Similarly, the Jacobian of G at a point, let's say y naught, so y naught is a point in N, is a linear transformation from the tangent space to N at point y naught to the tangent space to the manifold P at point G y naught. You can see here that we can actually compose these two Jacobians. The Jacobian of G of f x naught composed with the Jacobian of f at x naught will go from the tangent space to manifold n at x naught to the tangent space to manifold p at g f x naught. This is precisely the Jacobian of the composed function g composed with f at point x naught. I hope these are all clear. So in infinitesimal analysis, this is saying an infinitesimal change in the input will lead to an infinitesimal change in the intermediate value, will lead to an intermediate change in the output. If you compose the functions, it doesn't really matter. You are just mapping infinitesimal values to infinitesimal values. I really like infinitesimal analysis, but this really clears up the picture because you can see that Jacobians are just the linear transformations of these infinitesimal quantities. And these Jacobians are functions from vector spaces to vector spaces. Whereas just now you see Jacobians more in the matrix form, but matrices, as what we know, are linear transformations between vector spaces. So I just want to talk about this terminology called push forward. So Jacobians are linear transformations between tangent spaces. And so in the forward pass, where we are building up the computation graph, the Jacobians are actually pushed forward. And what we call the forward mode of differentiation is the push forward of Jacobians. One thing to know about this terminology, remember just now we have, let's say x, let's say it goes into some intermediate z and it goes to y, right? We have f and we have g. This lives in m, this lives in n, this lives in p. The Jacobian of f goes from the tangent space to manifold m at x to the tangent space to manifold n at z, and the Jacobian of g goes from the tangent space to manifold n at z to the tangent space to manifold p at y. In both graphs, we can compose the functions in the direction that the arrows follow, right? So we can compose g with f, we can compose the Jacobian of g with the Jacobian of f, and they are in the same direction, right? So this is exactly a push forward. Later we'll see its counterpart, which is called the pullback. But this is just for remembering, right? This is the push forward because they are in the same direction as the function composition. In forward mode differentiation, so this is just a side note. Again, I'll just draw a compute graph, but because we have seen it a lot of times now, I'm just going to use notes. In forward mode differentiation, what happens is we tweak some weight by delta x, and we try to see what the final delta L is. So this is precisely what the Jacobians are doing, right? So you can just imagine the Jacobian of this function. Let's say this node is f, the Jacobian of f composed with the Jacobian of g, composed with the Jacobian of h, etc. By composing all of them and acting on this delta x, which lies in the tangent space of the parameter set, it will produce us delta L, which lies in the tangent space of the real numbers, because loss lies in the real numbers, right? So this is forward mode differentiation. You'll often hear people talk about this thing called the Jacobian vector product, or JVP. So this J represents the Jacobians being pushed forward. This V represents the delta x vector. Or maybe I should write delta theta vector. This vector represents the delta theta, right? So it's some infinitesimal change or some infinitesimal change in the neural network weights. And we are doing a product because we are precisely doing the Jacobian composed together multiplied by the infinitesimal change in theta, and this should give us the infinitesimal change in output, right? So that's why it's called the Jacobian vector product. Now I will introduce, which number is it? 4. I will introduce cotangent space and pullback. Firstly, I will also introduce a covector. So what is a covector? I guess I didn't really define a vector, right? But this vector, you should think about it as all the infinitesimal changes that lives in the tangent space, right? Tangent space of some manifold. Think of it as a tangent vector. Yeah, it is actually precisely the tangent vector, right? So I should really write tangent vector living in the tangent space. What is a covector? For those of you familiar with linear algebra, a covector is precisely an element in the dual space, right? So recall all the tangent spaces are vector spaces. Vector spaces have its counterpart, which is called the dual space from linear algebra. So let's V be a vector space. The dual space comprises of the linear functionals on V. What does linear functionals mean? It means V star, right, is the set of F such that F is a function that takes in an element in the vector space V and produces a real number, right? And F is linear. Linear in the sense if you give it A plus B, it is equivalent to just acting F on A and adding it to F acted on B. I think when I was first learning linear algebra, it took me quite a long time to get this concept. But, in the machine learning paradigm, you should think, or even in linear algebra paradigm, you should think of linear functionals as linear scoring or measuring functions. It is basically saying, I present to you this element in V. Let's say I present to you small v in V. A linear functional is going to score how good that candidate is. Maybe it gives a score of 10. Now, if I give you 2v, right, you should expect the score to be 20. Basically, this functional is like a scoring function. You can think of it as a judge that says how well a candidate is. This is precisely the loss function, right? So note here, the loss function is precisely, okay, it is not linear, but it is a functional. It is a functional because it takes in a set of parameters or even a set of intermediate parameters if you start your computation graph from there, and it produces you a scalar output. And we all know that loss functions are also like a scoring or a measuring device for how well a predictor is. Okay, that's an aside from linear algebra, but back to the definition of covectors. The tangent space to M at X is a vector space. So it has a dual space. And that dual space is denoted as Tx star, right? Similar to how we denote dual spaces in linear algebra. This is the dual space or the cotangent space of Txm. A covector is an element in the cotangent space. In other words, it is a linear functional from tangent space to, let's say, the field, which for our purposes is the real numbers. Stare at this. It might seem a bit confusing, but again, you should think about linear functionals or like functionals as a scoring mechanism, right? So what a covector does intuitively is it scores infinitesimal movements. In our machine learning context, let's say this is our parameter space, capital theta, and our network starts at some point theta. There are so many possible updates. Let's suppose we take an update in this direction. This is given by delta theta. A covector, let's say in this case, denote by alpha, scores this delta theta. So it will score the movement delta theta and it will produce a real number. And just to hit back at one of the points mentioned earlier, right, we can denote this by actually the loss, right? So I'm just using this as a symbol to denote that it is a covector. We expect this dl to take in something in the tangent space of the parameter space at theta and give us a real number, right? It is measuring for any infinitesimal change at our current parameters, how well is that change? And how well that change is precisely governed by how much the loss changes. It is not the loss, but the difference in the loss with respect to the previous loss. And so I just want to make sure my terminologies are better. So we are very familiar with loss taking in the parameters of the neural network and giving us a real number. But the loss can also take in any set of intermediate values, right? Or intermediate activations. And it can also give us the value of the loss, right? So it is not surprising if we just feed in the intermediate activations and we just compute what the loss is. We can also give it the final loss, and the loss will just be itself, the identity, to make sure that we denote all these covectors properly, because there is some ambiguity here, right? What exactly is the tangent space that we're trying to score? So I'm going to denote this dl with subscript theta to represent that the tangent space that we are evaluating it over is the tangent space of the manifold that this theta is lying in, which is this capital theta. I hope this makes sense. So this dl is actually dl theta. Just to make sure this is more concrete, I'm going to draw in two other manifolds. This is the manifold of the intermediate z. Our theta produces z, and I'm going to draw in the loss manifold. The loss manifold is just the real number line. This is going to be 0, and this set of parameters will give us intermediate activation z. It will give us some loss, let's say L. With this, we can actually define three different covectors. We can define dl L of a delta dl, and this will give us a real number. This is precisely delta L. If we were to cut off the network at this final point, it's just going to return the loss itself. Two other covectors that we can have over here is dlz, right? It takes in a change in z and gives us what is the change in L. And the third covector that we can have here is dl theta. It gives us a change in theta. It gives us what is the change in the loss. And here is where I introduce pullback. Recall, let's say f is a function from manifold m to n. The Jacobian of f at a point x, where x is in M, is a function from the tangent space to manifold m at x to the tangent space to manifold n at fx. Therefore, we can also define its dual function, which is jfx star, to be the function that goes from the dual space t star fx n to the dual space, the cotangent space corresponding to the tangent space txm. Oh man, this is taking a bit longer than I thought. From linear algebra again. Let's say we have a function that maps from vector space V to vector space W. We can define its dual function f star to map from the dual space of vector space W star to V star, the dual space of V. And the understanding here is like, let's suppose we have an element in the dual space of W star, right? Alpha is in W star. What is alpha? Alpha basically takes in, by definition of it being in W star, it is a linear functional on W. So alpha takes in an element of W and it returns a real number or something in the field, right? Let's just suppose it's the real number. There is only one natural way to compose it, right? So just to make it more clear, let us consider a vector space V, a vector space W, and the real space R. We have a function that goes from V to W, which is precisely the function f. We have alpha, which is the scorer in the output space, right? It scores a candidate in the output space. Now suppose I want to score something in the input space. What can I do? Well, I can just transform it into the output space via f, and I score it. right? So alpha composed with F is a scorer in the input space, alpha composed with F. So there is this correspondence between this alpha here and the alpha composed with F. And that is precisely F star, right? F star maps a scorer in the output space to a scorer in the input space. By definition, F star of alpha will be equal to alpha composed with F, right? Alpha is something that lives in the space of scorer of output space, which is W star. And this alpha composed with F is a scorer in the input space. So it lives in V star. So F star is precisely going from the dual space of W to the dual space of V. So the point or the upshot is that, remember we said that Jacobians are the push forward, right? If we have f, g being two composable functions from spaces of manifolds, the Jacobian will be linear transformations in their tangent spaces. But because they are linear transformations between vector spaces, they have their dual functions, which is JF star. It goes backwards. It goes from the cotangent space of P to the cotangent space to manifold N to the cotangent space to manifold M. So what these arrows are saying is, given an infinitesimal change in P, we know we have a scorer function here. Well, we can pull it back, as shown by the example over here, to a scorer in the intermediate activations, right? Given a change in intermediate activations, how good is it? And then we can pull it back to the parameter space. Given a change in the parameter space, how good is it? So this is really pulling back scorers. So remember just now we have our DLL, we have our DLZ, we have our DL theta. These are all covectors. They are scoring mechanisms, with DLL being the identity functional, right? DLL is essentially 1. So this explains one of the mysteries. Why are we backpropagating starting from partial L equal to 1? Well, we are really passing in the covector, the scoring mechanism. Given a change in the loss will change by that amount. So we are passing back this scoring function or the sensitivity. This is being passed back to the cotangent space with respect to the intermediate activations, right? T star Z. And DLZ, it will take in a change in activation and it will output a scalar, which is how much should the loss change, right? This is a real number. Because we have passed back DLL as 1 as a covector here, we can apply the dual function of the Jacobian to get the scoring function in the intermediate layers. We can repeat this by composing it with the dual function of the Jacobian to get the scoring function in the parameter space. Given a change in parameters, what is going to be the change in loss? This should resemble what we have heard about in machine learning classes, just that I think the definitions in differential geometry really elucidates many of the confusions, because we often use derivatives and gradients interchangeably, but over here we note that we are really backpropagating the covectors or some sort of scoring mechanism. We are not propagating the gradients, we are propagating the scoring mechanism. So let me just write it over here as an exclamation mark. So in backpropagation, we are propagating the covectors, not the gradients. This is why in machine learning classes, we often see things like this. So partial L partial Z is equal to some Jacobian of the function transposed times partial L, let's say. Sorry, G here. And partial L partial theta equal to the Jacobian of F transposed partial L partial Z. Like the Jacobian here is obviously a matrix because we have given it some coordinates, right? But we should think about it as a function that transforms the sensitivity at the output to the sensitivity in the input. So Jacobian transpose is a function mapping sensitivity with respect to, sorry for poor handwriting, outputs to sensitivity in inputs. And it is not really a matrix multiplication, right? Like it is only a matrix multiplication because we have some coordinate system, and in that coordinate system, the Jacobian manifests as a matrix. And the transpose, we assume that it is the Euclidean inner product, which is why the transpose operation, which is actually the pullback operation corresponding to the ordinary Jacobian, is just the flipping of the matrix, right? The transposing of the matrix. And this is why we often see the sensitivity as the composition of the transpose of the Jacobians. I hope this also explains why the terminology here is called a pullback. So note, I've written here a pullback just to make it very clear, right? F goes from M to N, G goes from N to P. The Jacobian of F goes from tangent space of M to tangent space of N. The Jacobian of G goes from tangent space of N to tangent space of P. And the transpose goes in the opposite direction, right? It goes from the cotangent space of P to the cotangent space of N. And the transpose of the Jacobian of F goes from the cotangent space of N to cotangent space of M. And you see that the dual functions of the Jacobians compose in a way that is opposite the function composition, right? Function composition is going to be G composed with F. In the cotangent spaces, the mappings are composed in the opposite direction, which is JF star composed with JG star, right? So this direction is the push forward, right? We are going the same direction as the function composition, and this is called the pullback because we are going in the opposite direction. We learned that the backpropagation is pulling back the covectors, right? Or the sensitivity of the loss with respect to the input. In actuality, so in PyTorch, we have seen the .grad func, right? This should be rightfully called the pullback function. For a tensor, its .grad attribute actually doesn't store the gradient per se, right? It stores the sensitivity. So the question is, why are we updating the weights by sensitivities, right? So if you have been following along, we have our neural network parameters living in the space of theta. Any changes to our parameters should live in the tangent space of theta. But as we have discussed, theta.grad actually holds something in the cotangent space, which is T star theta at theta. Why are we updating our weights based on something that is in the cotangent space? Based on a covector? Well, we need to bring one more tool from analysis, which is called the Riesz representation theorem. In Riesz representation theorem, from an applied mathematician's perspective, it is saying in a space equipped with an inner product. I'm missing a lot of criteria by choice, right? Because I don't want to cloud this definition. But a space equipped with inner product, our typical space Rn, right? It can be equipped with the inner product, which is just the dot product. In a space equipped with an inner product, an element of V star in the dual space, so an element in the dual space can be identified as an element in V. An element in V star. So again, we should think about it as a scoring function, right? So consider a scoring function alpha that scores candidates in V, right? So alpha is in V star. There is an unique element U in V such that alpha evaluated on V is equal to the inner product of U and V for all V in V. So it is saying we can sort of mimic the scoring function alpha with an element in the original space V, right? It is just taking in the first slot in the inner product operation. Basically, this alpha is sort of equivalent to the inner product with its first slot already filled in by some element V. So alpha, remember, it is a function, right? It's a functional. It takes in some argument, but this is equal to the inner product of U with that argument, right? Both of them will produce U something in the field, right? A real number, for example. During our backpropagation, we have x dot grad or theta dot grad is equal to dl theta, right? It is the sensitivity of the loss with respect to theta. So this is a scoring function, right? Let me just be precise. It is saying given a change delta theta, how good is that change? And how good that change means how much does the loss change? Right, so theta dot grad is actually a covector, but a covector is a linear functional on the tangent space. So it can be identified by Riesz representation theorem as an element in the tangent space. And I am going to just tell you what the element is. The element is actually the gradient. The gradient as in nabla theta L. So nabla theta L, the gradient is definitely something that lies in the tangent space based on our understanding of it from calculus. I don't like to hand wave a lot of stuff, but in Euclidean spaces, let's say Rn, a tangent vector can be expressed or identified as directional derivatives. Does that make sense? So let's say we are on a manifold. Let's say we are at this point. There is definitely going to be some tangent playing over here, and we can express the directions in terms of the directions to take the directional derivative. Basically, what we want is a basis for the tangent space. We can take the basis to be symbolically the partial derivatives with respect to some set of coordinates, right? Partial x1 to partial xn. From this, we can take the dual basis. The dual basis is a basis for the cotangent space. In cotangent space, remember just now by our notation, dl theta is a covector. So I'm going to keep with the same set of symbols. We can express the dual basis as dx1, dx2, dxn. So remember, like these are covectors. Covectors are scoring functions of the input space. By corresponding basis, what it means is that for each covector, right, let's say dx1, it will only give a score of 1 to the corresponding base in the original basis, and it will give a score of 0 to all the others, right? So in mathematical terms, dxi, if you ask it to score the basis partial xj, this will be 1 if I is equal to j and 0 else, right? So it's precisely delta ij. What this means is that, let's say we have d theta is something that lives in the tangent space to the manifold theta at theta, which is our Rn space. So the tangent space to a particular value x in Rn space is actually isomorphic to Rn. My point is that we can express delta theta as the summation of delta theta I partial xi. This is precisely the decomposition of a vector into its basis, right? So I from 1 to n. Now consider the covector dl theta. dl theta, it is a covector. It can be decomposed into like a linear combination of the dual basis as well. So this is equal to the sum of I equal to 1 to n, right? Something times dxi, right? So what is this something? It is actually partial L partial xi. So remember that this dxi scores a change in the corresponding xi direction by 1, right? So the coefficient that is appended to it, how much we should weight the scorer is precisely the partial derivative of the loss with respect to that direction. And dl theta, when you give it the input d theta, this will give you partial L partial xi dxi evaluated on d theta, right? But dxi only cares about its corresponding basis. It only cares about partial xi. So this is equal to partial L partial xi dxi. We only care about the ith component, which is delta theta I partial xi. And the scoring of the dual basis on the basis is just equal to 1, right? And it is linear, so we can take out the delta theta I. This will be the summation of I equal to 1 to n partial L partial xi delta theta I. And this is precisely the inner product of the gradient and delta theta as a vector. The upshot is that dl theta can be identified as the gradient. This is like the result of Riesz representation theorem, right? And we usually call this gradient the Riesz representative of dl theta. In PyTorch, we have this optimizer function. And this optimizer function does the updates to the parameters of the neural network, theta. So theta t plus 1 is theta minus learning rate times theta dot grad. So implicitly, one functionality of the optimizer is that it converts the sensitivity of a parameter to a tangent vector of that parameter. So sorry, like my handwriting is getting atrocious at this point, but what I meant to say is that optimizer, right, in math form, you should think about it as something that converts a covector into a tangent vector. Usually, this is just the transpose operation. You would think that it is the identity operation, but covector and tangent vectors, right, is actually related over here by the transpose operation. But it also goes to show that you can customize your optimizer in a way such that you can dictate how this covector is being transformed into your tangent vector, right? For example, if you're not using the Euclidean inner product, this transformation is not going to be the identity or just the transpose operation. It could be multiplied with something else. So for example, in natural gradient methods, you would use the Fisher information matrix in this conversion. The nice thing is that by learning all these differential geometry terminologies, we can actually isolate what is confusing about backpropagation, and we gain more knowledge into what can be customized to explore more ideas. This is getting very close to the end, so I just want to write out the resolutions to the two confusions that I had. So resolution for number one. So number one was, why do we pass partial L over partial L equal to 1? And what is the significance of the 1, right? So the answer here is that 1 is the covector. It measures the sensitivity of a changing loss and scores it, which is precisely the changing loss. And because this 1 is a covector, it actually goes from R to R. It is actually mapping the loss to the loss, which is why it is 1. It is the multiplier here. In one dimension, a covector is just a multiplication, right? So it's a multiplication by 1. I guess that is obvious on hindsight because this partial L is actually a measurement of sensitivity as well. So maybe I could have seen it earlier. I think maybe the confusion was, why did PyTorch name it .grad instead of .sensitivity? The second point of confusion is, what is the meaning behind all the arithmetic somersaults that we did, right? You remember we talked about how we formulated some trace and we did some cyclic permutation to express it in inner products. So I think the resolution is we do that if we don't trust or we want to derive from first principles the Riesz representative corresponding to some input. As you recall, we expressed things in the form of inner product. So the first argument in that inner product is in particular the Riesz representative that we want to find. So in summary, I guess firstly we talked about backpropagation mechanism and we explored PyTorch. Specifically, we know that torch.tensor, it has a .grad attribute and a .grad func attribute. This grad attribute should really be a covector. It can only be interpreted as a gradient after the optimizer has converted that covector to a gradient. But in the backpropagation phase, everything should be interpreted as a covector. And this grad func is really the pullback or the dual of the Jacobian. So we have gained clarity into both of these attributes. Number two, we talked about the forward mode differentiation. We now know that this is just push forward of Jacobians. And in particular, this is why we often hear people talk about Jacobian vector product. It is just the composition of Jacobians in the forward mode differentiation. We start off with something in the tangent space like delta theta, a change in parameters, and we just compose Jacobians on top of it. This is in the direction of function composition, which is why it is called the push forward. We talk about backward mode differentiation, which is backpropagation. And we have seen how this is just the pullback of Jacobian transposed of sensitivities, right? Or covectors. And this is why you often hear people talk about VJP, which is the vector Jacobian product. So the sensitivities are usually regarded as vectors. I don't really like this acronym. It should actually be called the Jacobian transposed vector product. Because we are again applying Jacobian transposers and we are doing it in the reverse order because we are going from the back because it is in the dual space. We are saying if we have a scorer that scores a change in some intermediate variable, how does that scorer translate into the actual parameter space? And I guess finally, we have talked a lot about differential geometry, which is pretty nice, I think, as a field. I have never gotten to learn it in my undergrad years, but we have barely scratched the surface. We only talk about the definitions. And I guess the major learning point, at least for me, is that I love infinitesimal analysis. And even I took this long to realize that the x naught is living in a different space than delta x. Delta x lives in the tangent space at x naught. And there exists a cotangent space that measures the infinitesimal movements. And Taylor's theorem is really about the push forward of Jacobians, transforming infinitesimal changes in one tangent space to an infinitesimal change that lives in another tangent space. So I think this is all very nice. So thanks for listening and hope you had a good time.